When coal particles are injected with a hot blast into to a raceway, they enter an extremely harsh environment. Gas temperature reach between 1000 and 1200 degrees Celsius with intense turbulence. The particle only stay in the blowpipe for a few tens of million seconds. That's why high burnout in such a short time is only possible when we use fine PCI coal. Now, timeline 0 to 1 millisecond, that is very rapid heating. In the very first millisecond, coal particle hit the hot blast stream. There is no visible flame yet, but inside the particle, rapid changes are happening. Moisture evaporate and the particle temperature quickly rise towards 600 degrees Celsius. The heating rate here is extremely fast, on the order of 100 to 1000 of degrees per second. Now between 1 and 3 millisecond, devolatilization dominate. Around 35 to 45% of the coal mass is released as volatile gases, methane, carbon monoxide and hydrogen. These gases form a luminous flame envelope around the particles. Fine PCI coal, especially below 75 micron, releases a very large fraction of its volatiles in this short window. Now coming to the band of uh, 3 to 5 millisecond, here ignition and flame are the main activity. By 3 to 5 millisecond, the volatile cloud ignite. These processes produce an intense local flame and a surge of heat release. The car temperature rises to about 1200 to 1400 degrees Celsius, initiating rapid car oxidation. High volatile fine coal shows shorter ignition delays and a stronger flame intensity. This is the zone where most of the exothermic energy is released to sustain high temperatures. Now from 5 to 30 millisecond, 5 to 30 millisecond, the remaining solid carbon, the car continues to oxidize as the gas travels through the blowpipe with the velocity of 100 to 200 meter per second. Residence time is only 5 to 30 millisecond. PCI trials show that 60 to 90% of the coal is burned out by the time it exits the blowpipe. Any unburnt char is carried into the raceway where it reaches further with CO2 producing extra CO. Car combination is diffusion control and burnout time scales with particle size squared. This means having the particle diameter reduces burnout time to 1/4. PCI design standard therefore target 70 to 80% passing below 75 micron to ensure near complete burnout in the short raceway residence time. This table illustrate the data illustrate the effect of particle size. At 250 micron, burnout require more than 300 millisecond, far longer than the available time. At 75 micron, which is the PCS standard, burnout is achieved in about 30 millisecond. With 70 to 80% combustion occur in that band. At 25 micron, burnout is essentially complete in just 3 milliseconds. The smaller the particle, the faster and the more complete the combustion. So this is the overall finding. Now the residence time in the raceway is extremely short, as we all know, and in earlier also it discussed only 10 to 30 milliseconds are available. Coarse coal simply cannot burn out sufficiently at that window. Industrial PCI practice therefore specify fine grinding below 75 micron and limits the coarse fraction. Now these minimizes unburnt carbon, prevent raceway permeability loss, and reduces wear erosion and wear also. Now coming to the main takeaways, to summarize, coal in the blowpipe raceway undergo rapid heating and devolatilization, ignition and carbon all within 30 milliseconds. That we have, that is the main focus of discussion. Fineness is very critical because of all particle size squared law. Fine PCI coal achieve high burnout while coarse coal doesn't. Proper PCI design, including particle size, volatile matter and grindability, is essential. The result is high combustion efficiency, low unburnt car and a stable blast furnace operation.